we'll have a talk that involves technology that is very much rooted in the 20th century. Of course, semiconductors displacing vacuum tubes would still be a 20th century technology. Perhaps we will have those quantum computers at some point. But I'm not talking about information technology per se. This is energy conversion. So it's a very simple concept. There's no controversial physics. There are quantum mechanical effects and some interesting heat transfer effects that have been that would require a more modern approach. But the centenary is this year, and I really enjoy the history of science, so I'm going to inject that. There's also some political history that affected this field, and through the 20th century, it attracted billions of dollars of investment, not from private capital generally. It was governments working on this for various purposes. It is not to my knowledge, used today, but there's been an effort to revive it over the past decade. And that would have started at Stanford, and it didn't start with me. I think it's interesting. There's an interesting question then, how did it get started? What we're working on is wafer-scale fabrication, lithography, etching, but and possibly, in fact, much more modern techniques to nanostructure surfaces and materials that didn't exist. If you can go do a Google Scholar search on my name, a recent publication in Nano Letters should come up in a project with my student and several faculty and other students looking at an anode with a very low work function motivated by this. The anode material is graphene, something that wasn't a 20th century material. I remember graphite and pencils, some people may remember, not the Apple one on the new iPad. So what are we going to do applying this and essentially reinventing this simple concept in a way that is potentially cost-effective and could have many applications? And when you think of my field of MEMS, there's whole conferences on energy scavenging for Internet of Things, getting rid of batteries, but this is primary energy conversion that would be targeting watts to megawatts, depending on the scale. We may need quite a few wafers to do that. So what applications, I'll go through three of them, and the third one would be a major focus of efforts in Germany. Finally, I think there's a lot of research prospects. There's also been a startup out of the group that is a couple of PhD students teaming up over the summer. So thermionic emission can be understood as from a view of a lake on a summer day. You have essentially a vapor coming off. There's a vapor pressure of water. It's visible in this case. And the same thing happens in a metal. If you heat it hot enough, you start having things come up. Ultimately, the metal begins to vaporize, but in our case, we aren't going that hot. We're just interested in getting electrons off. So if you remember, you don't really need to understand too much solid-state physics. We have a Fermi level at absolute zero. All the states are filled up, and we're certainly not absolute zero. Temperatures in the hundreds or even 1,500 degrees centigrade. Okay, we need a very high source of heat, or we need a new material with a much lower work function. What do we then do? Well, we collect those electrons. We boil them off, and this is a thermionic diode energy converter, which has been the most focus of the Stanford work that I've been involved with. And those electrons are collected. This is kind of an artistic energy diagram showing that the anode has a different work function, and it's probably cooler. And there are words of emitter, collector, anode, and cathode, and the letter C would be on the wrong side in between these, but emission and collection, and if you look at our papers, we would use these interchangeably. So the anode and cathode, emitter, anode, collector, and the physics are very well understood. you have an output voltage that's a difference of work functions. There's actually, that's an idealized case. There are probably some barriers in there that would involve things that space charge and other kinds of energy barriers that would reduce that voltage. Work function differences are around the order of a volt, and depending on the temperature, this exponential will get you a tremendous current density. So you would have high current, low voltage, very similar to a photovoltaic cell in terms of how we deal with it. The physics of the emission is the Richardson-Dushman law. It would be nice to have a large difference, and there's a design that would depend on the temperature of the heat source, what work function you need on the emitter, but certainly going low on the anode is a good idea. That's been an effort in our group. There would be issues of heat transfer. You have possibly a very narrow gap, probably in a vacuum, and you could imagine radiative and other sources of heat, especially since you ultimately are going to be getting electricity out. You have wires on this, and you have heat losses through the wires. So it's a very simple idea. You should be able to get some energy out, and that is indeed the case. Edison is the coiner of the word thermions. He was looking at the incandescent light bulb, and he was studying the decay of the filament, and he put something in there. He was trying to collect soot, but instead he got current. And so since it was a hot thing, he coined that word in the 80s and of the 19th century. You have Richardson and his contributions that led to a Nobel Prize. You have a guy, Schlichter, in World War I, in the appendix of his PhD in physics at Tübingen, proposes a thermionic converter because he's doing Richardson-Dushman experiments on different materials, and he makes the proposal in 1915. And then actually the first practical one, the demonstration, was 1939 in the Soviet Union. Another not so good year in Europe, 1915 and 1939. But in the post-World War II era, you have huge investment in the US and the Soviet Union. One breakthrough was a guy who just passed away at nearly 100. Hernquist at RCA had a lit diode. He struck a plasma to deal with space charge effects, paid a price for that, and cesium is not the easiest material to work with, but this was actually something that was efficient enough to attract a lot of investment. So 1973, I'm in late junior high school locally, and a lot of things happening in the world. That was a long time ago. So I would like to pause and look at something that the IEEE in my field doesn't do. They transcribed discussion sections at conferences. And in fact, we not only don't transcribe them, we discourage any recording whatsoever, partly because we always have a keg for the audience and the participants, and a lot of discussions you don't want to, there could be things said that might not really make sense or be coherent. In those days, you had people like Hastopoulos, who ended up on the MIT faculty, making comments of what they were achieving in 1968. Now, 1968 was the peak of the space race, and that was one of the things that was driving this. And they had a lot of money, and they were getting a lot of progress. 20 watts per square centimeter, efficiencies of 15%. They were extrapolating to 30% heat to electricity. The issue from the NASA perspective was, okay, we're there, we've got to launch these, okay? And so, ruggedness, reliability is a very important part. And in fact, the Atomic Energy Commission representative on this panel said that don't bother. The power source was a nuclear pile. They had a lot of heat, and 15% is fine. Why bother going further? Okay, so this was the atmosphere and the driver. And in fact, people did some cool things even earlier. In the 60s, you have these so-called, we call them button thermionic converters. They're rather small. You see in this black and white photo a little butane torch on a thermionic converter, a couple of wires, and you're running a fan. Efficiency around 4.5%, and very simple and no cesium in there, no work function lowering, and that would just be a photo out, a great publicity photo by GE Research. So what happened? Well, the application here was space power. We were in a race to the moon and elsewhere. There was a lot going on trying to get long deep space missions and substantial amounts of power in orbit, more than what the solar cells could provide, and possibly on the dark side of the Earth. Soviets actually pushed further. They got a 6 kilowatt converter and flew it at the end of the Cold War on a naval reconnaissance satellite successfully. And after the USSR, I don't think there were a lot of things that contributed to the collapse of the USSR. I don't think these converters were significant, but what the cost was, I don't think they had good accounting of what the effort was to build these things. But it was certainly bleeding edge technology and not really manufacturable. We leased a bunch of them at the end of the Cold War and ended up flying them to New Mexico on a large transport plane. This is a picture of what, in the perspective, to have this Soviet technology show up in New Mexico. It's kind of like a Klingon warship landing in a Federation planet, and you're getting, and then actually they give you their reactor or something. You get to, you know, so they built a 2-story vacuum chamber for this. No nuclear power. They built optical heating and ran and tested this, and met the guy that was in charge of that. There were reports written that are not really easily found on the web, but apparently exist in libraries. They were not forthcoming in sharing what their tests were, but these were functioning devices that did survive the launch. This is not terrestrial technology. There is a lot of precision machining, lots of tungsten, lots of cesium, and it was a plasma diode. So what happened along the way would involve politics. We have in the US, not the collapse of the country, but Nixon decides space nuclear reactors are possibly something that can't be afforded in the post-Vietnam era. We have the oil crisis, and we have a revival of alternative energy sources, including a burst in thermionic funding, often linked to, again, space. Some people remember Star Wars, the idea of shooting down ICBMs from space. This is a way to put nuclear reactors up there and get lots of power. This isn't Silicon Valley. Bill Clinton's elected, no more Star Wars. Okay, the Thermionics guys are along for the ride, and there is a bunch of companies that are sort of trying to navigate through this. And finally, an organization you may or may not have heard of called DTRA, the Defense Threat Reduction Agency, has a report on the web, and they concluded that there wasn't any short-term path between all of this investment in space military thermionics and something that would be useful in this post-Cold War era. And they'd been provoked to do this by some people at Sandia who objected to that, but this report helped put a wet damper on things. So that was before, where were some of the audience in 2001, kindergarten, or that's a long time ago. So what I would like to do is look at the thermionic converters. I'll revisit that historical theme. Sometimes fields are developed and go on the shelf for various reasons. I've been on committees with reports of that sort, national academies, and you got to be careful in what you say in those reports, because you could be spectacularly wrong. In any event, the cathode work function is designed around the hot side temperature. There are different sources of heat. I'll mention some completely green ones, concentrated solar. There would be not so green ones that this might help in terms of efficiency, and there's a sort of 700 Kelvin times the work function in electron volts. So 1700 Kelvin, you subtract roughly 300 is a hot flame, that torch. And so you have a work function around 2.5 electron volts. That's rather easily achieved. The anode at 1.5 is not so easily achieved. And I'll mention where we are in that. There's a voltage in the gap that can be space charge and other regions that doesn't help. And remember, of course, you may be thinking, I have field emission and all, but we're not applying energy to this to manipulate things. We are just sitting there and going heat to electricity. So the goal ultimately is getting this DC power out. We have certainly considered pulsing electrodes and playing games, and that's something, again, that's a 21st century thing. So what do they look like if you look at the basic important things? Well, a typical historical converter, you really don't get a whole lot of efficiency until you get tremendously hot cathodes because you have a barrier index of around 2 electron volts. Remember, that's the sum of some of the anode work function and some gap voltage. If you begin to work on that, things get kind of interesting in terms of lower temperatures and higher conversion efficiency. And certainly if you get to around a 0.5 electron volt, you begin to be able to look at very nice efficiencies that would be very useful in a lot of applications, especially if you have a cold side temperature that's hot enough to run another cycle. So as a topping cycle is where this could be quite useful. So this is adapted from work by Hestopoulos and Giftopoulos, a couple of obviously Greek engineering profs at MIT in the 70s. And thermoelectrics are much more studied, huge investment in thermoelectrics. For those that know thermoelectrics, ZT of 10 is outrageous, right? People sweat bullets to get ZT of like 2 and or less. And so also the materials in thermoelectrics have great difficulty at very high temperatures. So the vacuum gap and these very simple materials tends to mean that thermionics gets into a position of potentially higher efficiency if you have the high heat source. And so ultimately you're competitive with these well-developed technologies or an assist to that in some cases. So my argument has been that we have something that's well worth looking at. I'm not interested if it's a $1 million gizmo, though NASA could use it perhaps to get more power out at Pluto. You could ride to Pluto with a nuclear pile. The materials issues of hugging a nuclear pile are also serious impediments to the people working on this, right? That they had things to deal with that were very challenging. I gave a talk on this at a fusion research center in China in the spring, and it's a different kind of radiation, and they would view this as yet another way to boost, if once they get positive, this is a way to get better efficiency out of a fusion reactor. This is a long-term project that's going to be not one group. It's going to take a major commitment to make this happen. It's wonderful to visit the fusion people who look at an even longer drive into mid-century. There are people whose whole career will be working in fusion, and just to indicate the effort, they were busy trying to deliver something to San Diego because China and Japan and Europe, there's an international test bed in San Diego, and efforts to get that moving further along. This could help. I've never seen a tokamak up close. It is quite a machine. So how to do wafer-scale thermionics? Well, not invented here. This is Don King, who was testing the tokamaks. It was a huge effort in MEMS at Sandia in the 90s. He wasn't personally involved, but I think you read the you know, Sandia is a big lab, but I think people are unaware of what's happening. It's always important to be aware of what your colleagues are doing in different parts of the university. There's some grad students that can actually be disruptive. So Don filed a patent and tried to get funding on basically something that would look like an early accelerometer, deep reactive ion etched silicon bonded together. He did some theory that said if you got a micron gap, you should be able to get 30%, no plasma needed, because you're too close. The space charge can't form. So there's some physics that work. He got the patent issued. It took a while. And it was filed not too long after the topazes showed up. I think when you have someone, you know, especially at Sandia, pushing for a significant program, that I think triggered, I don't know the exact causal relationship, but this committee looked at this Thermionic Converter proposal and said that basically there was a need for this tremendous temperature gradient, 500,000 Kelvin per millimeter, interesting units. You'd think it would be 500 Kelvin per micron, which is possibly challenging. I think it's more than that. The committee said that sustaining such an enormous temperature gradient with tolerable material, you know, thermal conduction losses is not credible. You have a thermal short circuit. Okay, and I can see signing off on that. And these were the DITRA people from the Defense Threat Reduction Agency. You can download it. It's a public report. In fact, there were no people from my field on it, because long before this, there had been something called a bolometer invented various places, an incredibly thermally isolated structure that would detect millikelvin temperatures and yet be anchored to a substrate. So the thermal isolation for this, in order to make an infrared camera out of an array of these, and there's a big push to get these into automobiles that would involve, you'll find my name, but mostly Tom Kenny in mechanical engineering, would be doing atomic layer deposition for incredibly thin bolometers structures. This is vanadium oxide, a very difficult material, and the goal is to get them cheap enough that every car would have a heads-up display with an infrared camera. My community is pushing hard so that here's something you may not know. I'm injecting from Planet MEMS in the Allen building. We would lose half of our night vision by the age of 40. And I don't know what the full curve is, but it is not in the favor of people driving at night. And of course, we've driven a lot, so we can edit in. We know what should be on 280. We don't necessarily see the deer or the people working on their flat tire or something. And to have that highlighted on the right heads up would save a lot of lives, including the animals and the people who roll trying to avoid the animals. So in any event, this is a major thing. They should have known about this. We can detect millikelvin, and so what do? Well, we want kilokelvin, not millikelvin, but it's the same basic structure, and this is a simulation in COMSOL by ex-postdoc Igor Bargatin, ex-PhD student Jay Lee, and you see temperatures of 1400 Kelvin and basically room temperature on the anchors, because you have something that is thermally floated off the surface. It has long legs and they're hot in the center, and there's a big thermal gradient. Now, will it move out of plane? You know, there's some interesting engineering. We made U-trough suspensions to make it stiff out of plane. Can't make I-beams easily, but we can make U-beams, and those are very stiff, even though it's made out of a very thin film. So in any case, it looks like it would work. Will it work? Well, we made something out of a material that's not a very good cathode, but it's a good platform. This is silicon carbide, LPCVD silicon carbide. It wasn't done in the Stanford nanofab because we don't have a silicon carbide tube, but it is available in Berkeley. So this grad student went up there, and you have this structure that's certainly suboptimal. The lithography isn't great, but it certainly is thermally isolated, and we optically heated it. So there's a series of things where this is in a vacuum chamber where we're looking through kind of a telescope to see this little pixel that's getting hotter and hotter and hotter and hotter, and it gets cooler and cooler. It doesn't care. The substrate's basically room temperature, and you're heating this to outrageous temperatures, well over 2000 centigrade and incandescence. So the whole DTRA committee I haven't contacted, but of course their cover story is they put that in there to provoke people, right? That, I mean, it's obvious idiotic comment, and they wanted someone to, rise to the challenge. If you're ever on a committee, you can always say that you knew better. Yeah. Yeah. Yeah, so it gets, we were able, with a blue laser, silicon carbide has a high band gap, but we were able to get energy into it just to demonstrate the thermal isolation. That isn't a thermionic cathode. You need to do more than that, but it is a start. That was a few years ago. So one question is, we can easily fabricate gaps from 100 nanometers and maybe even thinner to 100 microns. It gets harder if in microfab with wafer bonding. That's kind of the easy sweet spot. Do we want to make large gaps? No. If it's 100 microns, you're going to get space charge. You're going to get charge buildup across this gap. It's well known from vacuum tube days. Langmuir-Child law. If you get really small, that looked kind of attractive, but lately people have been looking at heat transfer in tiny, tiny gaps, and it turns out you get coupling between surfaces through the vacuum. It's kind of evanescent heat transfer, and so there's an applied physics letter that looked at this, and there's a lot of things that happen when you get close. You can have photons that reflect, but then couple to the other side if you're in a close enough gap, and you get heat across. You can have near field perturbations, all kinds of different things that we modeled and borrowed models from the community to see what the optimum would be. Well, normally in engineering, Murphy says the optimum is inconvenient, just on principle. In this case, he's asleep because, in fact, the optimal is exactly where we would want to be. In your pocket would be much more elaborate silicon gyroscopes and accelerometers with massive numbers of comb fingers and spacings that are all in the range of a micron. And so this was excellent news. The efficiency, it's all, 60% is a idealized 1D model. It's the area where we want to operate. We don't want to be where the Russians were, which was over here at 100 microns, losing a lot of efficiency to space charge and having to do a plasma and not really recovering it. And if we get really close, then we also get thermal shorting. So that, I think, was a contribution to set the rules. So lately, Blair, now at Microsoft, Justin's doing a startup, and I decided to make a cathode for the sole purpose of actually testing anodes. So it was a second generation process where we would have holes to the backside for convenient optical heating. And so this shows a typical process, layers and lithography, but it's not electronics, it's MEMS, so things are a bit larger. And we're going to make a composite of tungsten and silicon carbide on the cathode, because silicon carbide doesn't have the right band gap, and tungsten is a standard, well-known cathode material. So what it actually looks like is kind of cool if you're into 3D micromachining. There's a hole underneath that wasn't quite perfectly aligned, you can kind of see, and we have this grid structure where we would put the tungsten and then this surface coatings of like barium, strontium to lower the work function further. And we would deposit those coatings using atomic layer deposition, not the kind of old school mortar and pestle kind of technique. So you would have something that you could crank out huge amounts of this. We haven't dense packed the pixels or anything. In fact, if you know MEMS, you probably want another layer to have, like the Texas Instruments mirror display would be an example of a two-level device with a tremendous fill factor. And with a single layer, you can't do too much. So in any event, we built these for the sole purpose of testing. Where we're focused lately has been on the anode. And I'll tell you, we is a lot more than my group on this. This is a commercial dispenser cathode, one of our test anodes on a heater stage. All of this goes into quite an interesting vacuum system in the Moore building in the Jabal Lab for Advanced Materials. Nick Malash has built this vacuum thing, and here it is in there running. It's basic materials research to try to see how this anode is going to work. This is going to take a long time if we are building this in an Edisonian way. And in fact, one of the things that's happened in the 21st century is computation. This is my student Sharon Chow, ex-student, she's a PhD, had a PhD in which she looked at these complex mixtures of things that you would coat to lower the work function. There's barium, strontium, calcium, and historically mixed up things, very, very complicated physics. And how do you optimize this without doing hundreds of experiments and having a decade-long PhD? Well, there wasn't much of a choice. In fact, in a polycrystalline case, you've got a lot of complex material transport and the electrons getting out of here. I'm just going to click through this because the shortcut is to compute it. And density functional theory is a standard way to, from first principles, not perfectly, but rather computationally efficiently, you can get the work function, you get formation energy. And so with her diving in with Jens Norskopf in chemical engineering in a group at SLAC, was able to gear up on this and adapt some code and end up using DFT, and there's some feedback loop of optimizing the pseudopotentials and all. There's some front work that's needed, but once you've got the machine set up, you are in business to do a whole bunch of calculations of work function and a proxy for formation energy. So these are triangular diagrams of mixtures of barium oxide, calcium oxide, strontium oxide, and additional materials that would, additional sort of dopants, lithium and scandium, complex thing. This is all computed, not measured. And in fact, you have both of these and 570 total compositions. This is a paper in Journal of Physical Chemistry. And the people doing this, all of a sudden you have an arrow that says, try here first, right? We haven't mapped all of this. We do have some literature that in selected parts of the space. But I think this is an example why it's good to be doing your PhD in 2015. Those of us who are doing PhDs in an earlier millennium wished we could have computed our way to accelerated experiments and actually get a paper along the way. It doesn't get any better. But in many cases, it was nothing but going in and grappling with things one step at a time. I think a really big breakthrough, Sharon was second author on a paper with Johannes Voss. How many of you have been to SLAC? I'm talking to the younger generation. Well, no, it's okay, but grad students and all. There are tremendous possibilities at SLAC that would include computer science and EE more than you might think. Just end of story. In this case, you have a bunch of people. Johannes had the idea that he could cleverly extend the boundary conditions, including the leads, and compute the emission current for the first time. For the very first time, from first principles, compute the Richardson-Dushman coefficient. And I think as we have envisioned new materials, you now have a platform where you can compute work function and the emission current. And so with some serious attention, and of course it's nice to have one of these computing clusters at SLAC that has a lot of cores, thousands and thousands, and we put them to good use. So in any case, where are we collectively? Cathodes are not the big problem. Tungsten, and with the ALD deposited nanolaminate from Sharon's PhD, we can get to 1.5 EV if we want to, or we could, in some cases, we don't need to go that low. There's been a lot of work at Vanderbilt and nanocrystalline diamond. The Richardson-Dushman coefficient, however, has to be very high. It's not enough to have a low work function, and a very low emission is possible. Diamond has been very difficult. There are bright spots on the surface, and a lot of it doesn't emit at all. So anode's a harder problem. Nemenich at Arizona State has a nitrogen-doped nanocrystalline diamond with 0.9 electron volts. That is very attractive. He is well aware of the thermionic implications of that. So remember, 0.5 is like a holy grail. 0.9 isn't bad. And Dan Riley filed his thesis in June. He has 0.7, but it's a surface photovoltage effect on a very surface engineered semiconductor. And I'll mention semiconductors playing a role in potentially the cathode as well. And that nano letter is, and I don't have slides on it because it just published, was the electrostatically doped graphene, where we use a field to pull down the work function, and we got to 1 eV with graphene. So that is a potential anode as well. So new materials make things much better. How do you vacuum encapsulate these things? Actually, that was a big problem for MEMS. If you want to make a good resonator clock, if you want to make a gyro, you want to have it in a vacuum. People know how to do vacuum, but do they know how to do vacuum at the wafer level in high volume? Well, Jay decided to, and we had a visitor from Japan, we did old school glass to silicon wafer bonding to seal up some cathodes and see if we could run them in a kind of a demo. And yes, the vacuum wasn't ideal for this, but we have under glass an encapsulated structure. The gyros in your phone are absolutely 8-inch wafer going to 12-inch wafer, wafer to wafer bonded, sealed and produced in a commodity. In this case, we have to be careful. There's high temperature seals. We have to seal ideally on the anode side where it's not so hot. There's certainly some materials that would be needed. In the 60s, there are people around who were there in the development of thermionics. They said the vacuum seals were a major problem. Once they got them fixed, the reliability was not an issue. So we would have some input from the early technology. Now, in much of my career, the core device is always wonderful, but if you pan out, you have wires. And interconnects and contacts are the bane of everything. So are we actually having something that's great, but you can't actually get any current out? Well, it's nice that other people are trying to go to very high temperatures. The EU has had a big project on high temperature gas turbine sensing, and we have a colleague, Debbie Sineski, in Aero and Astro, who is very motivated by Aero and Astro applications where MEMS sensors have to go to outrageously high temperatures. So here's an example of a indium aluminum nitride HEMT that's been running at 800 degrees. My students sometimes anneal things in furnaces at 800. This thing's operating at 800, and it has a very modest tantalum copper ohmic contact. I don't show the one in this Electrochemical Society paper where they had the metallization was screwed up and didn't work. It was completely destroyed at operating at that temperature. So actually these materials could be not so much of a problem. I would point to a collaborator at Berkeley, Roy Maboudian, and her student Fang Liu. They looked at a contact that would use a new type of nanographitic carbon between silicon carbide and platinum. And their contact, really the limit of their furnace is 540 degrees. And the normal contact is beginning to fail. But what's really shocking recently is that they would run this in air. And so it's not in a vacuum at all. It's a very, things are oxidizing at hundreds and hundreds of centigrade. This, the carbon is not susceptible to that. They've sort of demonstrated, I think we can get the current out. So a lot of pieces, and have we really put it together yet? Well, I will tell you more when we wrap up. What are the commercial applications where this could work? J.C. Zhao is at Department of Energy, and this is a 2008 version of a chart that would show sort of cost versus capacity in kilowatts and also efficiency. And some of our favorite things like gas turbines are quite good if you are powering a small city, not so good if you want to get energy that would be at a smaller level. MIT had a microturbine project, but micro is relative, and they are certainly going to have challenges in this 1 to 10 watt range. So we think there could be small-scale applications. The ones on the right, we possibly could add on top of that extra efficiency, and I'll mention some of those applications as well. So where will this possibly be useful? There's a lot of heat in the world. Sometimes we go to great lengths to heat things to very high temperature. We should consider insulation as a scavenger, right? We can be insulating and pulling energy out. The humble water heater, the Department of Energy would like to turn into a cogen plant. If you could do something better than the kind of cogen that would involve reciprocating engines, and so it would be nice to get a kilowatt out of your water heater, and that isn't perfectly green because you would get it by burning more natural gas, but it would have a net, ARPA-E has published what the impact of that would be. They had a call for proposals that would have a pocketbook impact on the person or apartment owner, individual house or apartment, and it would reduce carbon emissions, and it's just an all-around win. It's not perfect, but you would use that flame. In the back east in the winter, you could be running that all the time. The waste heat, of course, is your hot water. And right now, you're only making hot water. So it's a distributed power solution. Some people are obsessed with efficiency, and certainly these are designed in a way that is optimum. Modern aircraft, I think the 787 was called the first really electric airplane, getting rid of a lot of hydraulics. So there are generators on those planes, on those engines that are producing tremendous amounts of power. Again, a thermionic converter could change the way you design the combustor and the entire engine if you're getting significant power out of the hot zone. So and of course we have our concentrated solar where there's no shortage of high temperature and a real incentive to boost the efficiency of those plants. There's existing heat engines, but the temperature on that surface of that graphite, which is actually black without illumination, but is heated to well over the temperature that you can use in a normal heat engine. So the Thermionics converter would take the concentrated heat at the surface, and the reject temperature would be able to run the rest of the converter. So in any case, how does a water heater produce electricity? Well, you have thermionic converters in the burners. And I guess since these are in a closet or in the garage, it's nice that there aren't reciprocating engines with mufflers and all of this. You do have exhaust coming out. The target efficiency is not so high. The record thermionic converter is 22%. Okay, if you get to around 25%, it becomes very attractive to do this. Cornell did a study on the impact of super aggressive conversion to natural gas leading to a non-fossil future versus cold turkey going to the non-fossil future. They're almost the same. So this could be a bridge that would buy some time to get the more green solutions perfected. In Europe, Jochen Manhart gave a talk over the summer that was actually standing room only in material science on their thermionic converter project, which actually has a Stanford connection. This is a triode. You have an emitter, collector, and a gate. They propose using electromagnetic fields to stabilize the electrons so they aren't intercepted by the gate. A lot of elegant E&M. They have a paper last month in APL Materials on using graphene as the gate, patterned graphene. They've measured the transparency of graphene to low energy electrons, and it's about 60%. first time that's measured in very low energy electrons, and they have apertures in it. So again, a new material could be a game changer in terms of allowing you to build something that would otherwise not be so efficient. In this paper, which is a couple years old, I took this from Joken's site. He was using a laser-etched kind of milliscale grid. And so the target in Germany is coal-fired, not natural gas or oil, coal-fired plants. There's a lot of them in Europe. And this would be the topping cycle that would make them more efficient until they're ultimately turned off. But that may be a while. And so that could be a driving application. I think our focus has been ultimately on small-scale applications where we think something on the order of 100 watts to a kilowatt would be much more attractive. What would you do with 100 watts? I'll mention in a minute. That's kind of that's like your laptop battery with full on calculation. Why not just use a battery? I'll expound on that a little bit. But what's interesting is there is a Soviet Stanford connection that actually motivated my getting into this. The thermionic diodes and triodes at Max Planck and the work in my group and Nick Melosh's and ZX Shen's group all derived from a paper in 2005 by B.Y. Moises and T.H. Jabal. Okay, and it was a proposal for a new kind of thermionic converter, a theory paper in the Journal of Physics D. And who were these people? Well, Boris passed away just 3 years after that at a very old age. He was the head of the Soviet thermionics program. He got out of the Soviet Union after the Cold War collapsed, and he went to McCulloch building at Stanford to be a research associate with Ted Jabal, who's actually still around. I sat next to him in the standing room only talk. I knew about it ahead of time. My students were all, plastered around the periphery. And Ted is very much into thermionics now, thanks to Boris. And one of the things that would be interesting is to see a US patent application involving the Germans at Max Planck and the lead guy, Ted. Who retired a while ago. In fact, GLAM, the Jabal Lab for Advanced Materials, is named after him, but he has an office in McCulloch and would be interested in the triode since he's contributed to that. So this is not necessarily wafer-scale technology, but it is, as someone interested in the history of science, that is to me, a fascinating proposition. So fascinating historical connection. And we've looked up conferences where, of course, it's in Cyrillic, it's in Russian, headed by Boris in the 70s. So 21st century application, if you look in Spain, there's the original grid-qualified solar plant. Now, these are very large installations. That's a very large tower. And lately, they've been doing storage by heating molten salts and running turbines at night at a reduced load. So this is always giving power to the grid. More interesting, locally outside of Las Vegas, just in the California side of the California-Nevada border, in a place that has almost no one there. I don't know why, Ivanpah, I don't know if there are any residents there, but there's a 200+ megawatt solar concentrated solar plant that would have these big towers. And in fact, the people that designed this, BrightSource, is a company up in Oakland. They are only wondering whether thermionics is a 2020 or 2030 kind of technology. In one of our papers, we estimated that you would basically be at coal cost for generation if you could add a really optimized thermionic boost to this. So they are very much interested in that. So lastly, I'd like to look at some really radical innovations that have come out of Nick Melosh. Nick Melosh And I didn't make the connection. When I got into it, there was a former colleague of ours, Peter Pumans, and I put in a proposal to this after seeing Ted's paper. Peter's now at IMEC. And so that was circa 2007 or so. And actually, Nick, I emailed him because I knew he'd done some cool diamond work, and I thought diamond might be good for thermionics. So typical faculty, we go meet, 2-hour meeting, have a blast, and he convinces us diamond isn't ready. Because not only do the other diamond guys don't understand, he doesn't understand it. There's a lot of things with diamond that are really cool, but not really ready for a device, for EE kind of applications. Well, that night, after that meeting in March of 2008, he goes home, and being significantly younger, I think kids, toddlers get put to bed, and then I get this email at 3 o'clock in the morning, and it's this very long email where he proposes using a semiconductor instead of a metal. Now, having taught with Jim Harris EE216 these kinds of band diagrams, and why on earth wasn't this thought of? Sometimes, you know, the most obvious thing is sitting right in front of you. It's rather complicated physics. It's not a photocathode. It's a photon-assisted thermionic process, and there's a Nature Materials paper that goes into the details of this process, where you have to only get over the electron affinity, so it could run a lot cooler. You don't have to go all the way into from the p-type Fermi level up, because you can get partially boosted into the conduction band. You need light for this. Straight thermionics, as we call the thing that you put in your water heater, doesn't need the photons. But in that concentrated solar, you have plenty of photons and the heat, so you have an opportunity to design something that could boost the temperature tremendously, and it loves to be hot. You need the heat to get over. It's not a photovoltaic cell. Remember, it is a vacuum gap. Dan Riley's PhD put a semiconductor on the anode. So the whole thing is now part of semiconductor physics and has to be added if this really flies. And it can drop the anode work function and change the operating mode. What would happen then in a solar plant is that you have this concentrated solar flux that has a thermionic layer on top, and the back end is the same old good old steam run turbine that they would have already. And so it's just if it doesn't work, it doesn't, not much changes, right? But if it is working and you're getting electricity out of this hot zone, you have things in series, and if you're even at 25%, unlike computing, where you have to get factors in order to make any impact at all, this could be quite interesting. There are a lot of materials challenges. Jared got his PhD on the topic in December of last year. So what are the research prospects for this? I think it's very attractive. I would be kind of an enthusiast. You know, you get bitten by different things, and there's a whole lot of objections. I was early into MEMS, and there was a huge amount of objections of things that would never work, and you know, all kinds of reasons not to do this. And I kind of have seen that kind of, you know, but I can see it's hard, but it certainly is doable, and the payoff could be quite huge. The use of photons could be quite attractive in the for concentrated solar, and it actually makes some things easier. The temperatures can drop because you have less of a barrier. But we know a whole lot more about materials processes than in the past, and I think that 100 years after the invention, there's a chance of running the bright source people need 1,000 square meters of thermionic converters that would be built in some kind of a hexagonal tile. Certainly ceramic frames, not 100% fill factor, but we kind of know how to do this sort of thing. And if you estimate the cost, it is of course quite affordable because we're very good at lithography and wafer bonding and things. So I'd like to hitchhike onto my MEMS efforts and also import the nano world's things. So who's working on this locally and beyond? We have one of the collaborators, Jim, who's contributed through the MBE to papers on the PEAT and the semiconductor anode. Jens is a chemie, but he's also at SLAC, is one of the great computational materials people. Piero Pianetta is at SLAC, NEE. The beamline at SSRL has been effective. ZX is an amazing Renaissance physicist, applied physicist, material scientist, former chief scientist of SLAC, has contributed. Nick massively. Roy at Berkeley is surface science and silicon carbide. And we've gotten collaborations with Jim's former student at UT Austin building materials, and NREL, Miles Steiner, has some good growth furnaces. So in any case, it's an interesting kind of effort to shake the tree with some new ideas and see if we can kick this off. So the students involved, a lot of them are no longer around, and I haven't put up the new ones, and the new ones did not make this talk because we actually have a group meeting tomorrow, and I think they have other things to do than hear the review. But Igor is at UPenn. He was born in Siberia, Moscow State undergrad, Caltech PhD in physics, who I think my role is to sort of make him an engineer, and he would be doing a lot of interesting materials in ME at Penn. Jay Lee teamed up with a student of Krishna Saraswat and has founded an infrared imaging company called Stratio. I think they've moved recently to San Francisco. Sharon is doing software for energy at First Fuel in the Boston area. And Justin's in a startup. Blair at Microsoft. Hong Yuan is the lead author on that paper on the graphene anode. And Jay Provine is a senior research associate who is in Fritz Prinz's group mostly now. So I mentioned the startup, and then so these couple of guys are not visible in here. Nick's group goes whitewater rafting. That's a bit dated picture because there's actually water in a river in California. You don't have to carry the boat downstream. Dan and Jared teamed up on something that was called M37 out of Lawrence Berkeley National Lab. It's now called Cyclotron Road. It's an idea that energy startups are not like app startups. You need patience and you need tremendous resources. So they're kind of incubated at a national lab, and there's 4 other little companies. You can read about them in the New York Times, and you can go to their website. They're trying to commercialize thermionics and have picked the name Spark Thermionics. So 2 physicists who actually have rubbed shoulders with material scientists and EEs. And I think it will be interesting to see how things go. So with that, I'd like to acknowledge the funding agencies. Okay, I'm going to click through them all because, as you can imagine, to restart something takes some effort, right? So you would see GCEP is a critically important at Stanford, historically for energy, the Global Climate and Energy Project. I had a DARPA center with companies involved that were very interested in this. It was I say was because it ended a couple of years ago, kind of a cost share matching thing. DARPA DSO has been interested for small scale photon-enhanced thermionics. The application, you have an inflatable concentrator mirror in your backpack. In the Sierras, you have a small thermionic converter that gives enough juice, like 500 watts, so you can run a cappuccino machine, which has to be lightweighted. And that is a application that could attract some interest from the community. You bring power, very lightweight, and no fossil fuels. And it doesn't work at night, but that may be okay. So in any case, the Moore Foundation funded ZX. Department of Energy has begun to get interested, and this has all been made in the mostly in the SNF, somewhat in Berkeley. And with that, I think I am out of time, and also open for questions. This goes for another 15 minutes, right? Which it means that I was out of time because I thought maybe there would be questions from people from different backgrounds who might be interested in this.
So in that picture, the RCA thing with the blowtorch, what was that material?
It was tungsten on the cathode and nickel on the anode with this clever bellows compression seal. Very simple structure. They didn't put cesium in it, but they did get a vacuum. And it was only 4.5%. But, you know, it's pretty cool.
In the zombie apocalypse, you can run your fan.
Yeah, of course, you got to have the torch. And if you look at the energy, you know, it's not a necessarily ideal situation. So, yeah.
Zombies. Yeah. Well, and what temperature do you need to drive that? I mean, would a candle do it, or does it really have to be a blowtorch?
Well, I don't know flame. There's actually people at Lawrence Berkeley Lab who is a sort of a combustion group, and there's another national lab, people that really know about combustors. Your combustor in your water heater is not designed for thermionics, right? And it would have to be rethought to get more radiant heat would help. Heat transfer is a big deal. And I guess the candle, I don't know quite what the flame would be. It's a lot lower than that torch. And that would drive the cathode work function down. It would drive the anode work function is going to have to go even lower. So you sort of get in this limbo situation. So it really works. I would think that a thermoelectric thermionic tandem would be a really neat thing. And we have a world leader in photovoltaics here. How would is there a mix where this sort of thing could be useful in conjunction with photovoltaics? I guess the game changer is that it isn't the applications focusing on something that would be consumer, relatively low power. You could tile them up to get a lot of power, and there would be some challenges in that. But I think there could be applications. Getting rid of batteries is a good thing. Japan had a large project on eliminating batteries in that would be supplying 10 to 100 watts because they are dangerous, right? You would have battery fires as a problem. Boeing 787 has a lot of batteries and they catch on fire, right? But if you replaced it with a fossil fuel thermionic battery equivalent, these little applications are not going to contribute epsilon to global warming, right? And they may contribute a lot to getting the reduction of the logistics trail of building batteries is also something that, once you have the battery, it's great, but you may need to rip up a lot of stuff and invest a lot of energy to get that, the refining and everything. It's a very simple thing that may be...
Also disposable batteries.
Yeah, and if you could really work on it, I guess the lithium polymer batteries that we actually use in the engineering 40M lab, which Mark Horowitz has created, this course. I don't know if any of you have intersected with it as students or TAs or section leaders, but the first lab is a solar powered cell phone charger, and the battery is a lithium polymer battery. And they're a little, they're getting better, but those are the batteries that you can't fly with. They won't even fly them on cargo planes. They have to be shipped, and they have a tendency when they drop to become unstable. My dad is a retired EE and model airplane aficionado, and he had a crash a couple of years ago. Got the battery out of the plane, walking back on this field, and one of his friends said, "Hey, your jacket's on fire." And the thing caught fire in his jacket, and lithium, he got it off quickly, but it's something that we know how to handle little bits of fossil fuels, and if you can beat them on efficiency, then you have something safer. Some people want to have highways in the sky with UAVs delivering pizzas and other things to dorm rooms, and if there's ever that kind of density of traffic with battery-powered operation, you know.
I saw a fuel cell powered by vodka, so maybe you could use vodka.
That would be another possibility. Actually, in our lab, we got a fire can for the LiPo batteries because you can't put them out with a fire extinguisher. We have a metal dustpan to scoop those LiPo batteries, get them in the can, and let them burn out. They'll do something in there and open it up, possibly with a chemical suit, breathing apparatus. They're fairly unoptimal technology.
So has there been interest in the automotive industry for this? Header temperatures certainly seem to be in the right temperature range, and with the interest in hybrids now.
So the question of could you actually go direct to electricity and get rid of the Tesla and have this good old Tesla pulls up to the gas tank, but you don't have any internal combustion engine, you have a torch, and it may sound cool. But it's in principle, that was an early, notice Bosch is on there. They make water heaters in Europe, and they do make a lot of automotive systems. I think the thermionic engine, you have a century of development in really efficient ways. In principle, you might be able to do a bit better, but it's probably better to fly, is where weight matters, and this could be an advantage. It's not, in that case, it'd be interesting to look at the life cycle of the Tesla battery pack and, and view that against something. It could be that, yeah.
As much the opportunity is maybe just general hybrid cars where you're going to be running an engine.
Anyway.
And unless you're braking, you're not doing any regeneration.
So you get rid of the internal combustion engine.
Well, you just use the waste heat from the internal combustion engine to charge the battery, as opposed to recharging the battery when you're just decelerating.
Yeah, kill the alternator.
So the waste heat of an engine is not that hot. The thermoelectrics might get up to temperatures where you could implement that. Thermionics, we have to get hotter. And so what you really need is a combustor that would be more like your water heater to go, that hot, to go direct to electricity. And there are issues with emissions if you are at those high temperatures,
You catalytic converter is several hundred degrees, 500 to 600 degrees, right? So not that far off.
Well, it's, it is, you could say it definitely, there's sources of heat that you might in the future be able to engineer the work functions and get some significant electricity out of. So it's a long march, right? Now the fusion people are on a longer, it is not a typical quick turn software consumer sort of thing. So the Department of Energy is stepping up to invest in energy startups, and Stanford did pretty well. They aren't all hardcore, technologies. A lot to do in energy with software married to existing infrastructure, and so those that are on the verge of getting out or forming startups, you might want to have a run at this year's cyclotron road. You do have to go to Berkeley and hang out up there. Red is not the official color of that institution. It's in West Berkeley, though, so you can live in the city and counter-commute, and yeah. So I think it is a start on complementing the venture capital, of reducing the risk, and maybe getting some technology that could go up the learning curve and make a major impact in carbon and efficiency.
Cool.
Yeah. So, questions from the audience. How many of you are EEs? Other engineer? Well, yeah, there are other engineering. Okay, this is EE 380, right? But
You never know what's going to show up.
so I'm teaching EE 412, which is advanced nanofab, and we have a mixture of people even outside engineering that would be into nanofab. Breakthroughs in surface science are highly relevant to understanding these effects to a degree that was inconceivable even 20 or 30 years ago. So I think the progress could be quite successful. And I mentioned the guy in Germany who is pushing hard. There's a European-wide project inspired directly from the Stanford Photon-Enhanced Thermionics project. In Asia, you would have individual faculty in China who are pursuing this. There's a lot of great cathode work in Beijing. They have recently collaborated with SLAC on cathodes, not for this, but for other things. So it's not like you're starting from zero. In fact, we are building on a tremendous amount of investment, and maybe it will finally pay off in a new century. So, any anything else? If not, thank you very much for your attention, and